Hello everyone, I'm Jiahao from Shanghai Jiao University, iPath Lab. Today I'm glad to share my work, Liquid State Drive, a case for DNA block device for enormous data. Let's start from the DNA storage basics. DNA, which consists of 4 different nucleotides, A, T, C, and G, is well known as the carrier of the genetic information. Today, with the advances of biotechnology, DNA can also carry universal information. Specifically, each DNA strand has its corresponding nucleotide sequence, so we use this nucleotide sequence to present information. Furthermore, DNA synthesis technology enables us to synthesize DNA of a specified sequence, and DNA sequencing technology enables us to read the nucleotide sequence of a DNA strand. With these 2 techniques, we can store and retrieve information in DNA. As a storage medium, DNA has 2 interesting advantages: high density and long lifespan. First, the DNA storage density is 10 to the 18th power bits per cubic millimeter, which is about 8 orders of magnitude than hard disk and 5 orders of magnitude than flash. Second, the DNA lasts for centuries, while SSDs and HDDs last for about 5 years. Besides, the DNA storage evolves at the pace rivaling Moore's law. DNA storage hardware consists of multiple chips, where each chip is a spot matrix. A spot is a test tube in which a large number of DNA strands are stored. The DNA strand is divided into 4 parts: the primer at the beginning and the end, and the index and the payload. We use the payload area to store data, and use the primer and the index to index the strand. Specifically, we use the primer to index the strand collection. An SC is a collection of strands that have a same primer in one spot, and all strands in the SC are sequenced simultaneously. To distinguish between DNA strands that are simultaneously sequenced within the same SC, we encode each strand's unique identifier within the index region. The DNA storage hardware supports 3 operations: write, read, and erase. For write operation, we first encode the binary data into nucleotide sequence, then synthesize the DNA strand with the corresponding nucleotide sequence, and finally store the strand into the spot. For read operation, we first sequence all the DNA strands in an SC to get the nucleotide sequence, and then we decode the nucleotide sequence into binary data. Due to the immaturity of the DNA modification technique, we need to erase before write, just like flash SSD. For an erase operation, we clear all DNA strands in the spot. After covering the DNA storage basics, a question arises: how to integrate DNA storage into current storage system? Our work focused on building a DNA block device. The block interface is one of the most crucial interfaces in storage systems. It is simple and enables us to random access data at the fixed size block granularity. Additionally, the block interface is general. It's widely deployed in various scenarios, including AI, cloud storage, and archive storage. So, we propose to build a DNA block device to integrate DNA storage into existing storage system. We start by examining a naive DNA block design and its problem. For a naive design, we first partition the storage space into blocks. First, we map consecutive strands into a block. Then, we assign physical block address to each block. Supporting block operation is straightforward. For reading, the read granularity of DNA storage hardware is an SC, containing about 1 million strands. To read a block, we have to read all blocks within the SC. For writing, the write granularity of hardware is a strand. To write a block, we just write the strand of the block. For updating a block, due to the erase before write, we need to perform erase operation. The erase granularity is a spot containing about 2,000 SCs. So to update a block, we first read all SCs in the spot, and then we erase the whole spot. Finally, we write the new and other blocks in the spot. For updating a block, we need to read and write 12 million blocks. It's extremely costly. To mitigate the update cost, just like SSD, a straightforward approach is employ out-of-place update to reduce the update cost. We provide the logical block address to users and employ a translation table, which translates the LBA into PBA to realize out-of-place update. The out-of-place update brings garbage, which requires to be collected periodically. To facilitate garbage collection, we typically record some GC metadata, including the reverse translation table, which translates the PBA back into LBA, and also the valid bitmap, which records the validity of a physical block. However, because of the EB scale data stored in the DNA block device, the metadata, including the translation table, reverse translation table, and the valid bitmap, are also in PB scale. As a result, metadata is difficult to store in traditional storage devices such as SSDs and need to be stored in DNA. However, storing the metadata in DNA brings challenge, which is maintaining the in-DNA metadata reintroduces costly DNA update. Specifically, for each write, we need to update the translation table entry, update the reverse translation table entry, and invalidate the old block. These three processes brings the costly DNA update back. To solve these challenges, we propose liquid state drive. Firstly, we employ dual translation layer to avoid updating the translation table. Second, we introduce symbiotic metadata to avoid updating the GC metadata. Third, we employ delayed invalidation to mitigate the cost of maintaining the valid bitmap. Next, we further examine the design details of LeakSD. We propose dual translation layer to reduce the cost of updating the translation table entry. Specifically, we also out-of-place updated the translation table. Therefore, we introduced another layer to supporting out-of-place update in the translation layer. And now we got two layers, the L0 and the L1 DNA translation layer. The L0 DTL is used to index the address of the L1 DTL entry in DNA, and the L1 DTL entry is used to translate the LBA into PBA. What's more, the L0 DTL is in GB scale, which means it can be stored in the fast SSDs, so the updating cost of L0 DTL is negligible. We propose the symbiotic metadata to reduce the maintaining cost of the GC metadata. First, we observed the GC metadata is always accessed with the block data. Second, we observed that the physical block is out of place updated, so there is no DNA update for physical block. Based on this observation, we store the GC metadata with physical block symbiotically to eliminate the DNA updates. Specifically, for a physical block, we leverage the unused area of the last strand to store the entry of the reverse translation table, which means we store the LBA of the physical block in its unused area. Additionally, we add an extra strand to represent the validity of this block. We call it the invalidated strand. The physical block is invalid if the invalid strand has been written, and it is valid if the invalid strand has not been written. With symbiotic metadata, the GC metadata is updating along with the physical block data in an out-of-place update manner. So we eliminate the DNA update operation when maintaining the GC metadata. Last, we introduce delayed invalidation to further reduce the overhead of updating blocks. In block updating operation, we need to invalidate the old block. So we need to first read the translation table to get the old PBA. Then we write the invalidated strand to the old PBA to invalidate the old physical block. This read operation is on the critical path of updating a block. As we mentioned before, the read granularity is much larger than that of write, so the read operation greatly increases the updating cost. To solve this, we delayed the invalidation to reading a block and hence remove this DNA read operation from the critical path of updating a block. For more details, please refer to our paper. Next, let's move on to the evaluation. In evaluation, we implement the system based on our simulator. There are three main compared systems. The LeakSD is our system. The cross detail is a block device which has 24 megabytes block size, and its detail is small enough to be stored in SSDs. The no detail is the naive design mentioned before. We use three metrics to measure the performance of systems. The read or write amplification is the ratio of the requested read or write volume to the actual read or write volume. The actual read ratio is the ratio of the requested read volume, which is caused by write, to the actual write volume. In microbenchmark, LeakSD reduced write amplification up to 7 orders of magnitude times compared to the no detail design. The actual read ratio of LeakSD is almost 0. Additionally, LeakSD reduced the read amplification up to 6,000 times compared to the no detail design. In real-world traces, LeakSD reduced the write amplification up to 3,000 times compared to cross-detail design. Additionally, LeakSD reduced the read amplification up to 7 times compared to the cross-detail design. We also evaluate the performance of different block size from 4 kilobytes to 24 megabytes. Generally, a block size of 4 kilobytes achieves the best read and write performance in real-world traces. In summary, we propose a holistic DNA block device design. The key idea is out-of-place update. The challenge is maintaining the in-DNA metadata is costly, and the key techniques are dual translation layer, symbiotic metadata, and delayed invalidation. Thank you. Any questions?